Hello students, now in this session we are going to study the simply supported beam with point load. We have a simply supported beam and a point load is applied at the center, and our aim is to find out the deflection and slope for this beam using the double integration method, right? So suppose the load is applied and the deflection of the beam is like this. You know that for simply supported beam, when the point load is applied at the center, suppose this is center C and these are points A and B, the deflection will be maximum at the center. You know that we have already read about this, that the deflection will be maximum at the center and the slope will be maximum at the suppose this will be theta max, right? So our aim is to find out y max and theta max for this simply supported beam, right? And the length of the beam is given to us, that is L, and this center point is L by 2 distance from the point A and L by 2 from the point B, right? So what we can do is we have to apply this deflection formula, double integration method. Ei d2y by dx is equal to minus x minus mx. So we have to find out first the bending moment. Here you know that from shear force and bending moment diagram, that you go to that chapter, shear force bending moment diagram, first we have to find out the reaction. What is the reaction at A and B? You know that when the center load applies is W, then the reaction at A point will be half, that is RA will be W by 2. We have already read in shear force bending moment diagram. And RB will be again half of the total load applied, that is W by 2. So half will be shared by this reaction and half will be shared by the other reaction, B reaction, right? Now we can take a section. Suppose I am taking a section here at a distance x. Now what is mx? Mx, that will be equal to W by 2 multiplied by x. So this will be positive W by 2 multiplied by x. So this is the bending moment, and this is valid between A to C, because after that there is another load. So for the another section, what is the bending moment at, suppose, this point, another point that is also from at a distance x from the point A. So that will be, now mx will be equal to, this is positive W by 2x, the moment of this W by 2 and the moment of this W, that will be equal to minus W, and the distance is x minus L by 2. This is x minus L by 2. So x minus L by 2, and it is valid between C to B, right? Now you know that this part of the portion C to B is also available in A to C, means we can divide this mx into two parts. That W by 2x part is valid for A to C and total part is valid for C to B. So what we can do is we can divide this moment, we can solve this equation into a once go through, so that this part can be valid for A to C and total part is valid for C to B. So what I am going to do is I am dividing this part into two parts. I am writing a dotted line here, so that this part is valid for A to C and total part is valid for C to B. So here I can write, now in one go we can solve this equation. Rather than solving for A to C separately and then for C to B, I am solving in a one go using an entire equation, and this part is valid for A to C and this total part is valid for C to B. So we can write minus W by 2x x and minus and minus plus W x minus L by 2. Here this part is valid for A to C and total part is valid for C to B, right? Is it okay? Now integrating once we will get the slope, integrating twice we will get the deflection. So integrate it, you will get the slope. So Ei d2y by dx square, dy by dx will be equal to integration of this will be minus W by 2 x square by 2, it will become 4, plus C1 writing, I am writing here because so that I can use this equation as it is, and plus the integration of this W x minus L by 2 whole square divided by 2, right? So this is the integration and this will give the slope, but C1 is unknown. How to find out C1? C1 can be find out using the boundary equation, boundary conditions. What are boundary conditions? Boundary conditions. Boundary condition is that at x is equal to 0, y is equal to 0. At x equal to 0, y equal to 0, right? And another boundary condition is at x is equal to L, y is again 0. At x equal to L, y is again 0, right? We have taken small l. So, but we have dy by dx, so once again integrate it so that we can get the value of y. So we can integrate it again. Ei dy by dx integration is y, and that will be equal to minus w x cube by 3, so it will be 12. Integration of c1 is c1x plus c2. This is valid for a to c, and entire is valid for c to b. So integration of this again, so w by 6 x minus L by 2 whole cube, right? So this is the value of y, deflection. So this is the deflection which we have to solve for C1 and C2. There are two unknowns in this equation. There are two unknowns, C1 and C2, and we have to find out C1 and C2 using boundary condition. Now put the first boundary condition that y is equal to 0 when x is equal to 0. So x is equal to 0, this becomes 0, this will become 0, and this will become WL by 2. So you will get finally C1. So put boundary conditions in this equation. So suppose this is equation number 1. In 1, what are the boundary condition? That x is equal to 0, y is equal to 0, and x equal to L, y is again 0, because there is no deflection at the supports. So x is equal to 0, y is equal to 0, x is equal to L, y is equal to 0, right? Put it in this equation and you will get the two unknowns C1 and C2. I am writing directly the value of C1 and C2. The value of C1 is WL square by 16. WL square by 16. This is C1. Solve it and you will get this value. Put the value here and you will get the final value. And C2 I am writing directly because it is a mathematics and you can solve it. So C2 will come out to be 0. C2 will come out to be 0 because this is L and this again L by 2, you will get L by 12 and this will cancel out. So you will get C2 is equal to 0. So C1 will be this, C2 will be this. Finally you will get the deflection equation as final deflection equation I am writing here. Now y will be equal to minus w x cube by 12 ei, this thing, minus w x cube by 12 ei. C1 value we know, so C1 value can be put here. So you will get plus w L square x by 16 ei, and this is valid between A to C. Remember this part we have written, right, which is valid between A to C, and plus w by 6 x minus L by 2, same thing, x minus L by 2 whole cube. Now one thing you have to remember that when you are finding C1 using this boundary condition, suppose you are using this boundary condition that x is equal to 0, y is equal to 0. This x is equal to 0 lies between A to C. So only this equation is required. No need to use this equation when you are using x equal to 0. So while using x equal to 0, omit this equation because this is valid for C to B and x is equal to 0 lies between A to C, right? So omit this equation when you are using x is equal to 0 is equal to y is equal to 0, first boundary condition, right? And when you are using second boundary condition that x is equal to L, y is equal to 0, x is equal to L lies in this equation C to B. So entire equation will be required. Because full equation is valid between C to B, right? So remember that when you are applying the boundary condition x is equal to 0, y is equal to 0, this term is not required because this part lies between A to C and the equation is valid between A to C, only this line, this part beyond the dotted line, right? So that's why there is a separation here, right? So this part is valid for A to C, entire part is valid for C to B. So this is the deflection for this beam, right? Now what is Y max? What is Y max? Y max is at x is equal to L by 2. Put y is equal to x by L by 2 and you will get the Y max, right? So put the value of, so Y max lies at x equal to L by 2. So put x is equal to L by 2 in this equation. Suppose this is equation number 2, and put into equation number 2, and whatever deflection we will get, that will be the maximum deflection, right? So Y max will be equal to Y max, put the value here and you will get the Y max, right? W L Q by 48 EI. So this is the maximum deflection, which is a very important term because that failure take place at maximum deflection, right? That's why we are writing the maximum deflection separately, right? At x is equal to L by 2 at the center, YC is Y max, right? And the slope is maximum at point A when x is equal to 0. So theta max or dy by dx maximum lies at x equal to 0 or x equal to L, right? So what will be the, put here in this equation, C1, put the value of C1, you will get the deflection, and by putting the deflection, you later on you will get the maximum deflection when you will put x equal to 0, right? So you can put here the value of C1 so that you can get dy by dx. So before that you can find out, before that, what is dy by dx? So before that you can find out the dy by dx. So dy by dx will be theta is dy by dx will be minus w by 4 ei. Ei can be taken right hand side in denominator. So minus wx square by 4 ei plus C1 value we know now, wl square by 16. So plus wl square by 16 ei, right, plus, and this is valid between A to C, plus this term is available always, w by 2 x minus L by 2 whole square. So this is theta, slope. So this is another equation, slope as a function of x. At any point you can find out the slope, right? So this equation number is 3. This is equation number 3, the slope, right? So put the value of C1 here, C1, and you will get the answer, right? Now theta max lies at x equal to 0 or x equal to L. Put in third equation, you will get the theta max. When you put the value of x as 0 or L, right? So that will be WL square by 16 EI. So this is the value of theta max. So what we have done in this question is, we were given with a simply supported beam with point load at the center. A simply supported beam was given with point load at the center, and we have to find out the deflection and slope at a function of x and the maximum deflection and maximum slope, right? We know the maximum deflection is at its center and maximum slope is at the supports A or B. Now we have deflection equation ei d2y by dx square is equal to minus mx. We have taken two mx here. One is valid between A to C, another is valid for C to B. So we are divided into two parts. This part of mx is valid for A to C and this part is valid for C to B. Entire part is valid for C to B. And only beyond this line to left of this dotted line, the validity for A to C. We have integrated it, we get the slope, C1 is unknown now, and again integrated it, we get the deflection. Equation number 1. Now the boundary condition is applied that at x is equal to 0, y is equal to 0, x is equal to L, y is equal to again 0. Put the value of this boundary condition in this equation and you will get the value of C1 and C2. When you are putting x equal to 0, y is equal to 0, this is valid between A to C, because this point is coming between A to C, here only, at A point. So A point, you have to use only this equation, not required, this equation is not required. Right hand side of the dotted line is not required for this boundary condition, x equal to 0, y is equal to 0. When you get C1 and C2, put again in this equation, you will get the value of y. Put again in this equation, slope equation, you will get the value of theta or slope. When you get y and theta, you can find out y max and theta max. When you put y equal to x equal to L by 2 in this equation, x equal to L by 2, you will get y max. And when you put x equal to 0 in this equation, theta equation, you will get theta max. So this is how we can find out the deflection slope for a simply supported beam loaded with a point load at the center.